Welcome to the AI on AI podcast, where we explore the cutting edge of artificial intelligence and its implications for business and technology leaders. Today, we're diving into a fascinating innovation called fractional reasoning via latent steering vectors. Joining me are a panel of experts to unpack this paradigm-shifting approach to inference-time compute optimization for large language models. Let's kick things off with a high-level overview.
Absolutely host. Fractional reasoning is essentially a framework that allows us to dynamically adjust the reasoning depth of large language models, LLMs, during inference. It's like having a dial to fine-tune how much brainpower the model uses for a given task. Traditionally, inference time strategies like chain of thought COTI prompting or majority voting apply a one-size-fits-all approach.
That's a great start. Expert in ML, can you elaborate on how this latent steering mechanism works?
Sure thing, host. To put it simply, when you prepend a reasoning instruction like think step by step to an input, it induces a shift in the model's internal representations or its latent states. Fractional reasoning identifies this shift, called a latent steering vector, and reapplies it with a tunable scaling factor. Think of it like adjusting the volume on a stereo, except here, the volume controls how deeply the model thinks.
That's fascinating. Expert in business strategy, what are the implications of this for business leaders?
Great question, host. From a business perspective, the ability to dynamically adjust reasoning depth is a game changer. Imagine deploying an AI system in customer support or financial analysis. Simple queries can be handled with minimal compute, while complex problems receive a deeper level of reasoning, all without over-provisioning resources. This not only reduces operational costs, but also enhances user experience by delivering faster, more accurate results.
Excellent point. Let's dive into the technical details a bit more. Expert in AI, how does fractional reasoning improve existing test time compute methods like best of n or majority voting?
Great question, host. Fractional reasoning enhances these methods by introducing flexibility. For example, in Best of N, where the model generates multiple responses and selects the best one, fractional reasoning allows each response to have a different reasoning depth. This increases the diversity and quality of the outputs, making it more likely to find a correct or optimal answer with fewer samples.
If I may add, the framework also supports depth-based strategies like self-reflection, where the model critiques and revises its outputs. By adjusting the reflection strength, fractional reasoning enables fine-grained control over how much the model reevaluates its answers. This avoids pitfalls like overthinking, which can degrade performance, or underthinking, which leads to incomplete solutions.
That's incredibly insightful. Expert in ML, I understand this approach was tested across multiple benchmarks. Can you share some of the results?
Of course, the framework was evaluated on datasets like GSM 8K for math problems, Math 500 for advanced mathematics, and GPQA for general-purpose reasoning. Across the board, fractional reasoning improved accuracy compared to standard prompting methods. For instance, on the GSM 8K dataset, applying fractional reasoning to majority voting increased accuracy by over 5%.
That's impressive. Expert in business strategy, how do you see this playing out in real-world applications?
The potential here is vast. For example, in healthcare, an AI system could dynamically adjust its reasoning depth based on the complexity of a diagnosis. In retail, it could optimize inventory predictions by fine-tuning its analysis for different product categories. The flexibility to allocate computational resources intelligently opens up new avenues for AI-driven decision-making and problem-solving. It's not just about doing more, it's about doing more with less.
Excellent, let's touch on the challenges. Expert in AI, what are the limitations or hurdles in implementing fractional reasoning?
One of the main challenges is identifying the ideal scaling factor, or alpha, for each input. This parameter controls the strength of the latent steering vector, and its optimal value can vary depending on the task, the model, and the input. Currently, the framework uses a simple approach like majority voting to aggregate outputs across different alpha values. However, developing adaptive policies to dynamically set this parameter in real time is an open area of research.
Another challenge is interpretability. While the latent steering mechanism is highly effective, understanding the exact nature of the shifts it induces in the model's internal states is still an area that requires more exploration. This is crucial for building trust in AI systems, especially in high-stakes domains like healthcare or finance.
Those are valid points. Expert in ML, what's the next frontier for this technology?
One exciting direction is integrating feedback mechanisms to dynamically adjust the scaling factor during inference. For example, the model could use a reward function or consistency metrics to fine-tune its reasoning depth in real time. This would make the framework even more adaptive and robust. Another avenue is extending this approach to multimodal models, where the latent steering vectors could be used to balance reasoning across text, images, and other data types.
That's a great segue into the future. Expert in business strategy, how should organizations prepare to leverage this technology?
Organizations should start by identifying areas where dynamic reasoning could provide a competitive edge, be it in customer service, logistics, or strategic planning. Investing in infrastructure that supports real-time inference and scalable compute will be key. And of course, fostering a culture that embraces innovation and experimentation will help businesses unlock the full potential of fractional reasoning.
Wonderful. Before we wrap up, let's bring in a bit of levity. Expert in AI, any amusing anecdotes from the development of this framework?
Well, during early tests, we jokingly referred to the scaling factor alpha as the Goldilocks parameter, too low and the model underthinks, too high and it overthinks. Finding the just right setting was like trying to tune a temperamental piano. It took patience and a bit of luck.
That's a great analogy and a perfect note to end on. Thank you, experts, for this enlightening discussion. Fractional reasoning is clearly a transformative innovation with far-reaching implications. To our listeners, thank you for tuning in to AI on AI. Until next time, keep exploring, keep innovating. The paper introduces a new framework called fractional reasoning for improving reasoning efficiency in large language models during inference time. Fractional reasoning adjusts the depth of a model's reasoning based on the complexity of each input. This approach avoids the limitations of fixed prompts, which apply uniform reasoning regardless of task difficulty. It operates by identifying and applying a latent steering vector, which modifies the model's internal representations. The steering vector captures the effect of reasoning-inducing prompts, such as step-by-step reasoning. A scaling factor is applied to this vector, allowing fine-grained control over the intensity of the reasoning process. The method supports two reasoning modes, breadth-based and depth-based. Breadth-based reasoning improves diversity and quality of outputs, enhancing methods like majority voting and best event. Depth-based reasoning improves iterative refinement, such as self-reflection, to enhance correctness without overthinking. The framework requires no additional training or fine-tuning of models, making it model-agnostic and training-free. Experiments were conducted using benchmarks like GSM-8K, Math 500, and GPQA, which test multi-step reasoning tasks. Fractional reasoning consistently improved accuracy across models and tasks compared to standard test-time compute methods. In one example, the method improved performance in reasoning tasks by dynamically adjusting reasoning depth for each query. The framework avoids overreflection, which can degrade performance, and underreflection, which can lead to incorrect answers. Limitations include the need for predefined reasoning directions and the inability to automatically select ideal scaling factors. Future directions include dynamic adaptation of reasoning strength based on real-time feedback during generation. This method demonstrates a novel approach to leveraging latent representations for more efficient and adaptable reasoning in language models.